All right, so now we're going to throw a few more complications into everything. And this is called limiting reagent. And I think it's not a really hard concept if you really take some time and think about it and pay attention to the examples I give you. And also, this first example where I'm going to talk about bikes, I think it's really helpful if you think back to this example. It can sort of help you because this is a simple example. Apply what we're doing later on to this, and hopefully it will help. So, what is the limiting reagent or limiting reactant? Well, it's the reactant that gets entirely consumed, gets used up when the reaction is finished, when the reaction goes to completion. Not every reaction has exact amounts of A and B. If you put the two things together, they don't always react exactly and use up both. It's a very rare chemical reaction where that happens. You'd have to be really careful to do that. It's possible, but generally speaking, one or the other of your reactants there's more of than you need. So the one that gets used up completely is called the limiting reactant. It limits how much of the product you can make. So yeah, the limiting reagent ultimately determines how much product can be made. So for example, let's say you're trying to make some bikes. Well, every bike requires one frame and two wheels. So what if you have what if you have 20 wheels, but you only have 5 frames? How many bikes can you make? Well, hopefully you can already see that you can only make 5 bikes. That limits how many you can make. So you can I'm going to go through the steps in a minute, and then I'll refer back to this when I'm doing the chemical equations. But let's think really carefully it's pretty intuitive, I think, when you see this. I've got 20 wheels and 5 frames. How many bikes can I make? Well, the process that you're really going through is you're saying, okay, with 20 wheels, since I need 2 wheels for every bike, I divide by 2. That means, and that's your multimole ratio. There's 2 wheels for every 1 bike. So I take 20 wheels, divide by 2 wheels per bike, and I can make 10 bikes from those 20 wheels. I have 5 frames. I need 1 frame for every bike. So from 5 frames, I can make 5 bikes. So again, in each case, without the other, I could make 10 bikes out of the wheels. I could make 5 bikes out of the frames. But in this case, because we're using both quantities together, I can only make 5 bikes because I only have 5 frames. The frames will get used up before the wheels. And I know this is a simple example, and you're thinking, yeah, duh. But really try to think back to this example when you're doing the chemical reaction, and it applies because you're going to use up one, the other will be left over. Okay, so in this case, the frames are your limiting reactant because you can't make more bicycles unless you have more frames. So you're going to have excess wheels, and you're going to make 5 bikes. Again, keep this in mind when we talk about it later. And here's just another example. So we're going to make cheese sandwiches, and we need 2 pieces of bread and 1 piece of cheese for every sandwich. So in this case, you've got 6 pieces of bread, 2 pieces of cheese. So what's our limiting reagent? Well, it's pretty obvious. The equation is, again, two pieces of bread for every 1 piece of cheese makes 1 sandwich. We've got 6 pieces of bread, so from the bread we can make 3 sandwiches. We've got 2 pieces of cheese, so for every, we can make 2 sandwiches. So obviously we can make 2 sandwiches and then have 2 pieces of bread left over. Similar to the bikes and the wheels, you can figure out how many. Notice what I'm doing. I'm figuring out how much of the product I can make from one. I'm figuring out how much of the product I can make from the other. And then I'm seeing which one is smaller, and that's my limiting reagent. That's how much I can make. And then whatever else didn't get used will be left over. All right, so let's look at an actual chemical example. Zinc metal reacts with hydrochloric acid in this reaction that we looked at earlier. We've done in lab. You may have done it in lab. This would be lab C3. If you haven't done it already, you will be doing it soon. So zinc reacts with hydrochloric acid in this with this reaction. 1 mole of zinc reacts with 2 moles of hydrochloric acid to give us 1 mole of zinc chloride and 1 mole of hydrogen gas. Now, we're going to start simple. If I have 0.3 moles of zinc and I add it to 0.52 moles of hydrochloric acid, how many moles of hydrogen will I produce? Okay, so you might really quickly say, well, 0.3, because zinc is 0.3 and 0.52 is hydrochloric acid, and so that's it. But don't forget that mole to mole ratio. You need twice as much hydrochloric acid as zinc. So what you're going to have to do is you're going to have to figure them out each separately, figure out how much hydrogen I can make from the amount of zinc I have, how much hydrogen I can produce from the amount of hydrochloric acid I have, and then whichever's smaller, that will be how much hydrogen I can produce. All right, so 0.3 moles of zinc, because it's a 1-to-1 ratio, will make 0.3 moles of hydrogen. Great. 0.52 moles of hydrochloric acid, though, because I need 2 moles of hydrochloric acid for every 1 mole of hydrogen, I need to divide by 2. So I can only make 0.26 moles of hydrogen gas from 0.52 moles of hydrochloric acid. And that's where often things get forgotten. We need to be able to convert from one to the other using that mole to mole ratio. So obviously in this case, if I have 0.3 moles of zinc and 0.52 moles of hydrochloric acid, all of the hydrochloric acid will react to form 0.26 moles of hydrogen. At the same time, most of the zinc will react, but not all of the zinc will react. So our limiting reagent will be the hydrochloric acid. And how much can we make? 0.26 moles of hydrogen gas. So you're going to have to take both into account, and you cannot forget that mole to mole ratio. Of course, it gets even more complicated if you're starting with grams to grams. This was the simple one-step method because we're going from moles to moles, but it's the same process. Now, the theoretical yield of a product is just the maximum amount of product that can be obtained from the given amount of reactant. So in that last example, my theoretical yield was 0.26 moles of hydrogen gas. The theoretical yield, how much can I theoretically yield given the problem? So what we just did is once you know the limiting reagent and you determine how much product you can produce with the limiting reagent, what you're finding is the theoretical yield. What's the most product that you can make? All right, so what is the limiting reagent when 3.5 grams of copper is added to a solution of 6 grams of silver nitrate? So that's the first question. And then how many grams of silver can be formed? So in other words, what's the theoretical yield of silver? So you're going to be able to find both of these out doing this problem. So you can see here that I've sort of written what I know. I know that I have 3.5 grams of copper, I have 6 grams of silver nitrate, and I want to know what's my theoretical yield, how much silver can I produce in grams. The copper nitrate's not important in this case. It could be in another case, but in this case, they're asking me for silver. And in the process, I'm going to figure out what my limiting reagent is. All right, so again, think of the process with the wheels and the bikes. You take the copper by itself and you figure out how much silver you can make from the 3.5 grams of copper. Then, in a separate calculation, take the 6 grams of silver nitrate and figure out how much silver you can make. Those will be the theoretical yields, assuming the other one is not present, but then when you put them together, the smaller one will give you your theoretical yield. Right. Now, whenever you do a limiting reagent problem, you'll always be given the amount of each of the reactants. And sometimes they'll just ask you, what's the limiting reagent? Well, in that case, you can figure out the amount of product either. It doesn't matter which product you pick. Just pick one and figure it out. And you can figure out the limiting reagent will be the same no matter which product you're going to find. Oftentimes the problem, though, goes on. So you can see in this question, what is the limiting reagent? But then look at the second question. It says how much silver can be formed. So it's just a hint, and you could figure out copper nitrate, but the second question doesn't ask you about that. So sometimes read ahead and just see, because you'd sort of waste time doing the other way, but what you want to know is silver. So you can kill two birds with one stone, as it were. All right, so again, here's our reaction. Let's take our copper, 3.5 grams of copper. We have to do our 3 steps. We have to first convert grams of copper to moles of copper, divided by the atomic weight of copper. Then we know that we're going to make 2 moles of silver for every 1 mole of copper, so we have to multiply by 2. And then we're going to multiply by the atomic weight of silver. 107.2 gives me, so 3.5 grams of copper will produce 11.9 grams of silver. Now we'll do the very same thing with the 6 grams of silver nitrate. This time 6 grams of silver nitrate divided by the molecular weight for silver nitrate, 169.9. Now in this case, it's a 2-to-2 ratio, so a 1-to-1 ratio. Don't forget to do it. I would just go through the motions of doing it, especially at the beginning, because you don't want to forget that step. In this case, it is 2-to-2, and so sometimes you luck out. So if you forgot to do that step, you would luck out, but you would not in the first step. So it's 1-to-1 or 2-to-2. Don't forget that step. And then again, you multiply by the atomic weight of silver, and you get 3.81 grams of silver, given the amount of silver nitrate we started with. So clearly, silver nitrate is our limiting reagent. You can't make as much silver with the 6 grams of silver nitrate as you could if you used up all the 3.5 grams of copper. So the limiting reagent is silver nitrate. How much silver can be formed? 3.81 grams. That's our theoretical yield. Even though we have enough copper to make more, we can't make more because we don't have enough silver nitrate. Sometimes people might do this and not do that third step, not multiply by the 107.9 for the first question. They might just convert to moles of silver, and you can compare them easily. And then for the last step, you might multiply by the molecular or the atomic weight to get the final mass. It doesn't matter. Either way, if you like order, this would be the best way to go. All right, so here's a second example. Let's say we have 5.1 grams of chromium, and it's heated with 9.3 grams of chlorine. What will the mass of chromium chloride be? What is our theoretical yield? How much CrCl3 can we produce? So again, 4.1 grams of chromium, I'm going to take the chromium and I'm going to figure out how much product I can make. So divide by the molecular weight, grams to moles. Then use the mole to mole ratio. We get 2 moles of chromium chloride for every 2 moles of chromium. And then multiply by the molecular weight of chromium chloride, and we can produce 12.5 grams of chromium chloride. If the chlorine gas was in excess, if we had lots of it, then we could make 12.5 grams. That would be our theoretical yield. But no, they told us how much chlorine we have, so we're going to have to figure that out separate. And that's just a good point. Sometimes you'll see a problem that says, what's the theoretical yield? And they'll say, this is how much of one thing you have and excess of the other. So you can read that as the excess would not be the theoretical yield. The one they give you is the theoretical yield. So in that case, you don't have to worry about the other one. So if you ever see that term excess, then you don't have to worry about it, because it's not the theoretical, it's not the limiting reactant. It's the one given to you. All right, in this case, 9.3 grams of chlorine, divide by the molecular weight of chlorine. Now it's 2 moles of chromium chloride to 3 moles of chlorine multiplied by the molecular weight of chromium chloride, and we can make 13.8 grams of chromium chloride. So again, what's our limiting reagent? The chromium is. What's our theoretical yield? 12.5 grams of chromium chloride. That's the most that we can produce. And what will we have left over? We'll have chlorine left over. Now, let's take this one step further. How many grams of Cl2 will be left over? Before I do this, let's think back to the bikes and the wheels, and follow that process. And you kind of, again, it's a little bit of a simple thing, but the process is what I'm talking about. So again, think back to that problem. We had 20 wheels and we had 5 frames. And so the question is, what's our theoretical yield? How many, in other words, how many bikes can we make? Which is our limiting reactant? Which one gets used up first? And then we might say, well, how many wheels are left over? So what we did, remember, we took 20 wheels. We divided by 2 because we need 2 wheels for every bike. And so we could make 10 bikes with the wheels we had. Then we took the frames, 5. That one is a 1-to-1 ratio, so we could make 5 bikes with the frames. So we determined that there were 5 frames. The frames were the limiting reactant because we used up all the frames. We could make 5 bikes. That was our theoretical yield. Now the question is, how many wheels are left over? So at this point, there's a couple of ways that you could go about it. You could say, well, all right, to make those 5 bikes, how many wheels did I have to use? I had to use 10 wheels. So if I started with 20 wheels and I used 10, I still have 10 left over. That's one way of doing it. So again, to make the limiting reactant, how many of the excess do you need to use, and then subtract to find how many are left over. Another way you could do it is you could say, well, I can make 10 bikes from these wheels. If I take away the 5 bikes that I'm making, I still have 5 bikes worth of wheels. Convert that back by multiplying by 2 because I have 2 wheels for every bike, so that's 10. So those are the 2 ways of doing it. I think the first one maybe makes a little more sense. You say, how many of what I have do I need to use to make the theoretical yield? And then, so that's what I'm going to do right here. So remember from the last slide that we figured out how many grams we could make. Chromium was the limiting reagent. So here's the second method that I was talking about. Okay, we can produce 13.8 grams using up the chlorine gas. We can make 12.8 grams 12.5 grams using up the chromium. So that means that we can make 1.3 more grams of product using the Cl excess. Then we just take that 1.3 and we convert it back to how much Cl2. So that's equivalent to saying, okay, I have 10 bikes worth of wheels. I used up 5 bikes worth of wheels, and then convert 5 bikes worth of wheels back to 10 wheels. So 1.3 grams of CrCl3. Now I'm going to have to, that's how much more CrCl3 I could make with the Cl2. But then I have to convert that back to Cl2. So again, divide by the molecular weight, use the mole-to-mole ratio back to chlorine, and then use the molecular weight of chlorine, and I would have 0.87 grams of chlorine left over. Here's the other method I was talking about. So alternately, we could say, well, okay, my limiting reagent is 12.5 grams of CrCl2. So how much of this Cl2 do I need to make it? So I take that 12.5 grams, which is my theoretical yield of CrCl3, convert that back, divide by the molecular weight, use the mole-to-mole ratio to find out how much chlorine that's equivalent to. So in other words, I'm figured out that to make 12.5 grams of chromium chloride, my limiting reagent, I need to use up 8.4 grams of chlorine. Well, how much was I given? I was given 9.3, so if I subtract the 8.4 that I need to make it all, I'll still have 0.90 grams left. That's a little bit of rounding error difference, and so it's pretty close. So it's the same idea. So whichever method you like the best, either figure out how much excess product you can make and then convert that back to the reactant, or figure out how much of the excess reactant you need to use up and find out how much of it is left. All right, a couple more topics. Percent yield. So here's the thing. When you're in the lab, reactions are not theoretical. You spill things. You don't have proper conditions. Not everything reacts the way it should. So the reaction may not be complete. You never can collect as much as you think you can. You can't scrape every drop. And so usually we're not going to get as much as we theoretically can. So what we usually report in the lab is called the percent yield or the percentage yield. And that's just the actual yield. In other words, let's see, I did the work and I got 10 grams. And then you divide it by the theoretical yield, which is what you calculated, and you can find out what percent of the theoretical yield you actually yielded. So percent yield is the actual yield, the amount measured in lab, divided by the theoretical yield, how much you could possibly totally make, times 100%. So in the last example, we determined that our theoretical yield was 12.5 grams of chromium chloride. Well, what if we actually ran that experiment and we collected our chromium chloride, we did everything exactly what it said. We used the same amounts of chromium, the same amounts of the two reactants. And when we finished our reaction, we collected 10.6 grams of chromium chloride. What's the percent yield? Well, it's just the actual yield, 10.6, divided by the theoretical yield, how much we could possibly make, times 100%. So we collected about 84.8%, about 85% of what we could have. And that's a pretty good ratio in industry. They try to get, of course, closer to it as 100% as possible, but you're never going to get 100%. All right, so what should you be able to do at the end of this chapter? You should be able to calculate the formula weight given a formula or a molecular weight given a molecule. Again, that's just a difference in wording. A formula is technically an ionic compound, and a molecule is actually a covalent compound. But either way, be able to find the formula or molecular weight. Be able to convert moles to grams or grams to moles of any substance. Actually be able to convert to number of atoms as well. Calculate the percent composition from the formula. Determine the empirical formula from the percent composition. Determine the molecular formula from an empirical formula. Be able to relate quantities in a chemical equation, which is things like finding the limiting reagent, being able to tell how much of one you need to go with the other, and then calculate the theoretical yield and be able to calculate the percent yield.